Okay, YouTube, in this video we're going to be looking at forming what we refer to as a matrix equation from a linear system of equations where we have the same number of equations as we do variables. So essentially our goal here is going to be to take a linear system like the one we see right here and solve it, but by first writing it as what we call a matrix equation. So let's go ahead and take a look at this linear system, and what we're going to say is the matrix form of this very same system here. And so in terms of the matrix form of a system, what you could see is that we have on the left side of this equation here, we have a 3 by 3 matrix being multiplied by a 3 by 1 matrix. And of course this is defined because our inner dimensions match, but what we get is a 3 by 1 matrix as a result. And so if we were to actually multiply this out, what I want everybody to see is that essentially to find, say, the first row, first column entry of this matrix here, we would have to multiply the first row times the first column of this. And what we get is A1 times X plus B1 times Y plus C1 times Z, and that would have to be equal to D1. Well, that's exactly what this equation says over here. A1X plus BY 1Y plus C1Z equals D1. And likewise, if we were to actually pursue this with just say maybe we could do the second row, first column, which would be this D2 here. We could say A2x plus B2y plus C2z equals D2. And of course, that's our equation that we see here. So what we're going to see, at least in the matrix form of a system, is this. All of these values we see here, A1, B1, C1, A2, B2, C2, A3, B3, C3, these are what we have as our system's coefficients. So this matrix on the left here, we're going to refer to this as very carefully here. We're going to refer to this as our coefficient matrix, the coefficient matrix. And we'll call this A down here. As far as what we put in this 3 by 1 matrix, well, this 3 by 1 matrix, you can notice that it contains our variables in our system, or the things what we're trying to find in the first place. So we say that this matrix contains the system's variables, and on the right side of our matrix equation we have a 3 by 1 matrix, but it says this matrix contains the system's constants. So to write a matrix equation, really, we could see that we get this coefficient matrix times a variable matrix gives us the constant matrix. And so looking at all of these together, what we're going to do is represent them symbolically by saying that our coefficient matrix we tend to write and label as the matrix A, whereas our variable matrix, because it is full of the things that we're trying to find and we do not know them, we'll refer to it as our X matrix because that's the matrix we want to go get by itself. And then lastly, we would say that B is our constant matrix over here. So we say that a specific example of a linear system in its matrix form might be this down here, where we're not talking about symbols up here, but instead of, symbols, a particular system. If we look at this, how could we write a matrix equation? Well, the way this works is because we have 3 equations and 3 variables, our coefficient matrix is of 3 by 3 order. We can see that all we do is drop in the coefficients 1, negative 1, 1, 0, negative 2, 1, negative 2, negative 3, 0. And so dropping in the coefficients, we see that our variables here were x, y, and z. We'll write our 3 by 1 matrix here, x, and that's populated with x, y, and z. And then last but not least, we say our constants over here, 2, 2, and 1/2. That's our constant matrix that this equals. So we want to get really good at writing these as matrix equations, because what we're going to be focusing on here in just a moment is how in the world, how with a matrix equation could we get x by itself here? And really the question is going to become, well, how do we get rid of this matrix A here so that x is by itself? And you might think, oh, we'll divide both sides by A, but guess what? Matrix division, not defined. We don't do it. So what are we going to do instead? Panic? No. What we're going to do is we're actually going to solve for and use A inverse if it exists. Because let's face it, if we had a matrix equation, A times some unknown populated values, matrix here, x, equals B, then we could say that to undo A, what we'll do is we'll multiply both sides on the left-hand side by A inverse. Now note that it says that multiplying both sides by A inverse would undo our A, but it says because matrix multiplication is not commutative. That means that the order we do it in is important. We have to put A inverse in the same left position on both sides. So to left multiply by A inverse on the left here, we have to multiply by A inverse on the left side of the right-hand side of the equation. So the neat thing about this is we know that anything times its inverse gives us the identity. And of course we still say that the identity times x here is equal to A inverse B from the right. But the neat thing about the identity also is anything times the identity is itself. So we really have isolated x here. And we could say that in general, if we have a square system, as many equations as we have variables, And as long as A inverse exists, which is this inverse of our coefficient matrix, then we can always say that the solution to a matrix equation, okay, or at least that represents a system, is the inverse of the coefficient matrix times the constant matrix. So in general, if AX equals B has a unique solution, then X equals A inverse times B. We can use that to solve a system of linear equations. So basically, to solve a system of linear equations, all we do is take A inverse times B to find X. So what we're going to do here is this. We are going to, first of all, we are going to write a matrix equation that corresponds to this system of equations right here. So let's start with this. We got to get our coefficient matrix in here. Looks like it'd be a 3 by 3, so we have 1x, negative 1y, and 1z. We have 0 x's, negative 2 y's, 1 z, negative 2 x's, negative 3 y's, 0 z's. So now to put in our variable matrix here, well, our variables are x, y, and z, and we know that if we multiply these out, we should get this 3 by 1 matrix over here that contains our constants, 2, 2, and a half. So for this system right here, what we want to do is solve it by using A inverse. Well, what we have essentially here is this. We have a matrix equation where A times the matrix X gives us a matrix B. So what we're going to do is we're going to say X equals A inverse times B. And so according to what is suggested here in this video, hey, all we have to do is take the inverse of A times B. So the way we're going to do this here is we got to first find the inverse of A. Now, to save some time, as a matter of fact, what I'm going to do is I'm going to type this into my calculator. So what we'll do is we'll put in our coefficient matrix here. We'll go to matrix, edit, A, and it's a 3 by 3, so we have a 1, type in a 1, a negative 1, and a 1 in our first row. We have 0, negative 2, and 1. It looks like negative 2, 3, 0. So we already indeed have this in here. I just want to check it out. If I pull out my matrix A, here's our matrix A. What I'm going to do is I'm going to type in A inverse times our matrix B, except for we haven't typed in B yet. So now let's go back over to matrix, edit, and we'll go down to B. And B in this case is a 3-row, 1-column thing. So we say 3 rows, 1 column. What we're going to do is populate it with 2, 2, and 0.5. Or you know what? I'm going to write 1 divided by 2. 1 divided by 2, and I'm going to let it do its thing there. It's going to write 0.5. So we'll quit out of this. And so essentially all we have to do is type in A, and we'll hit our inverse key here, A inverse, x and negative 1 key, and we'll say times our matrix B. So we do have to go back in and get B out. But once we do this, what we get is this 3 by 1 matrix, and what I want to be clear on is x equals 1/2, negative 1/2, and 1. So we get x equals this matrix here, 1/2, negative 1/2, and 1. And so since that's the case, let's recall something here. Our x matrix really was equal to this matrix here, x, y, and z. So in terms of what conclusions can we draw about the solutions to a system, we could say that its solution occurs at the point 1/2 is its x value, negative 1/2 is its y value, and 1 is its z value here. So pretty easy to find a solution to a system of equations by using a matrix equation and then just having A inverse taken times B. That if it exists, should exist as this matrix right here. Cheers.